Right. Hello and welcome, everyone. It's good to see you all. So this is so we're now around the middle of B term, and I'll just mention one thing, which is that although B term has been extended through, I think it's December 16th, because we had a speaker during the A to B term break, we will not have a speaker during that last week. So the last seminar for this term will be on December 8th. So with that, I will turn it over to Kubra Karayahis, who's going to introduce today's speaker.
Thank you. Hello, everyone. Thank you for joining today's seminar. It's my pleasure to introduce Professor John Allison as our guest speaker today. Professor John Allison is currently the William Hosford Collegiate Professor of Material Science and Engineering at the University of Michigan, where he is the director of U of M, the DOE Center for Predictive Integrated Structural Materials Science. He also has been serving as a technology leader for ICMA efforts within the Lightweight Innovation for Tomorrow. He received his PhD in Metallurgical Engineering and Materials Science from Carnegie Mellon University, and MS in Metallurgical Engineering from Ohio State University, and BS in Engineering Mechanics from the US Air Force Academy. He previously was the Senior Technical Leader at Force Research and Advanced Engineering, Ford Motor Company in Dearborn, and where he worked for 27 years. During his work at Ford, he received 204 technology awards, and he has over 200 publications and 5 patents. Previously, he was the 2002 president of the Minerals, Metals and Materials Society, and is the member of National Academy of Engineering, fellow of TMS and ASM, and was the past member of the US National Materials Advisory Board. His work today will be on integrating theory. His talk will be on integrating theory, simulation, and experiment to accelerate predicted materials science. So with that, let's welcome Professor Allison. I'm going to stop sharing, and it's all yours.
Great, thank you, Kubra, for that nice introduction, and Adam as well, and thank you all for the invitation. Let's see here if I can figure out how to share my screen. Can you see that font? Okay. Oh, how'd that come? Is it sharing?
Yes, it's sharing now. You can see.
Let me just move these silly icons around so I can see what I'm doing here. Okay, there we go. So at any rate, again, thank you. I'm pleased to be here. I wish I was in person, but certainly this makes scheduling easier. And so at any rate, I'm pleased to be here and to talk about one of my favorite topics, integrating theory, simulation, and experiment to accelerate predictive material science. So I wanted to start off with this aging curve for aluminum alloys, which is probably known to many of you, a series of aging curves. This is courtesy of a friend in at Monash, JF Knee. So at any rate, here's aging curve typical for aluminum, 4 copper, and then we start adding 10 magnesium. We get up here to silver, magnesium, silver, and lithium. And we've accelerated aging and increased the peak hardness substantially, over about a factor of 3. Now, what's interesting about these alloys is that this alloy was the engine block, the crankcase, if you will, for the Wright Flyers. And this was the wing structure for the 777. And so the point is, it took us over 85 years to add 0.3 magnesium, 0.4 silver, and 1 lithium and get that into application. And so, you know, it takes typically 10 to 20 years to develop a new material, and we just have to do better. You know, society needs this. Global warming is, of course, an issue, so we need to develop materials more rapidly. And global competitiveness requires us to do everything faster and cheaper. And so as a materials community, we just need to up our game a bit. And so in 2011, the Materials Genome Initiative was launched, and the purpose of that initiative is to do just that, accelerate the design and development, discovery of new materials twice as fast and at a fraction of the cost. And it does that. It proposes to do that with advanced experimental tools, advanced computational tools, and digital data, and that forms this materials innovation infrastructure. And so we were very fortunate in 2012 to be able to define and launch a new center here at Michigan that we call the Center for Predictive Integrated Structural Materials Science. And that's what I'll talk about today, to try to meet the challenges, if you will, of the Materials Genome Initiative. So this is a flow chart for integrated computational materials engineering, where we do manufacturing process simulation, then we simulate microstructural evolution, property evolution, and then have manufacturing history sensitive models of properties into product performance analysis, like crash or durability or what have you. And we have that capability. We can rapidly develop new products or innovate. The problem is this middle. This is sort of the missing middle, if you will, in our field. We don't have a core set of tools outside of CalFAD to do this. And so what we proposed and continue to propose is that that we would establish these extensible scientific core software and use cases for ICME for structural metals, and in that way rapidly insert the latest science into the engineering process and sort of be next generation ICME. As I said, this was established in 2012, so we've now have 8 faculty and 4 research staff, over 22 graduates. I think about 9 or 10 of them have PhDs have graduated. It's roughly $23 million over that roughly 10 years. So we're very fortunate to get DOE BES support for that extended period, and we're very appreciative. And this is a picture of the PRISM's folks when we could all be together 2 years ago, 3 years. So this is our leadership team. So a number of faculty at Michigan, as well as Anton Vanderveen at Santa Barbara, and some names that I hope you recognize and people that you know. And then we also have 4 staff members to make sure that the software is professionally developed with high standards and so forth. And so they really are critical to our success. So we have 3 thrust areas. As I said, computational tools. We also have a thrust we call the Materials Commons. It's our knowledge repository, if you will, and collaboration space. And then we integrate this in use cases using our integrated science. So basically our motto is open source and open science, and that's a way to accelerate predictive understanding. And this is our framework. It may look a little complicated, but I'll walk us through this. It has purposes. So the white boxes here are our PRISM software. So this is all open source, available on GitHub. Of course, we don't have all the tools, don't have the resources to develop all the tools, and many of them we don't need to. So we have our statistical mechanics is linked with VASP and Quantum Espresso. That's sort of the engine behind that. We also use dislocation dynamics code from Lawrence Livermore, Paradis. And of course, molecular dynamics is very important for us as well. And so there we use LAMPS. And so we have integrated linkages, some places very formally and some places a little bit more human in the loop. Of course, experiments are essential to any attempt to accelerate our understanding. And so we do a lot of experimental work, whether it's in the microstructural evolution or in the mechanical behavior arena. And so we sort of go from atomistics over here to sort of mesoscale modeling with phase field, and then eventually to crystal plasticity to measure the mechanical behavior. Another important tool here is Materials Commons. And so this is our collaboration site and where we reposit all of our data. And so all of this is is available to the field. I keep getting lost here where my cursor, there I am. Okay, so the open source software, as I said, so we have 4 primary codes: density function finite element based, so it's real space DFT. Statistical mechanics package, CHASM, for doing the Monte Carlo type activities that you need to do to get phase diagrams and energetics, temperature effects. Then we have Prisms PF, our phase field code, and then finally Prisms plasticity, our crystal plasticity code. All of these are really advanced codes meant to be used in high performance computing system. And they are hierarchical and integrated, and again, open source. And so these are all very, when we benchmark them, very computationally efficient and so forth. Since we started keeping track, we've had about 3,000 unique clones of the software. So that's roughly, we think, 3,000 users, roughly spaced equally with the different codes. Again, these are all GitHub based. A lot of activity on documentation and training and so forth. And we have annual workshops and mailing lists. And during COVID, since we couldn't have workshops, we did video training modules. So you can find us on our own YouTube station and get training for all of these tools. I won't go through the details of all the tools so I can get to some of the science, but these codes are updated annually. And so DFTFE came out with a new GUI-based or GPU-based, it should be, algorithm. CHASM has a brand new release, many new features in Prisms PF. We're certainly, and then also Prisms plasticity. One thing I want to mention here is Prisms fatigue. I won't talk about that today, but that's a new thing that we did with Dave McDowell at Georgia Tech that we're very excited about. And of course, this is all open source, which means open source development community is certainly invited and encouraged. And so I'm pleased that Kubra and Adam are working with us to do an implicit solver with our Prisms PF team. So that's we're looking forward to seeing that develop and mature. So thank you for that. All of these tools are also being integrated with Materials Commons. So if you do a run on Prisms PF, it's automatically uploaded, if you wish, to the Materials Commons. And then you use that in a private repository and then publish it when you so choose. Okay, so getting to the science. The science is where we integrate our experiments and simulation to try to advance understanding. And let's see here. I guess I'm supposed to ignore this thing, aren't I? And so we have chosen to do this around magnesium, where we have individual use cases around microstructural evolution and mechanical behavior. We chose magnesium as sort of a demonstrator because magnesium alloys are an important material of choice for lightweighting of vehicles, whether that's in automotive or aerospace, for improving emissions and saving fuel. However, I can't see my slide right now because of the poll in the middle here. To expand applications in those domains, property improvements are required. And magnesium alloys are a little bit immature. Typically, alloys are ternary alloys of magnesium and aluminum, and either manganese or zinc. Certainly there are other alloys, but these are the lion's share. When you compare that to an aluminum alloy or nickel alloy, it may be 10 elements. And so there's a lot of opportunity for improvement in magnesium alloy technology. And so we thought that that was a good framework, plus lightweighting fits the DOE needs. So our use cases are shown here. We've evolved this since 2012. A lot of work, early days on precipitate evolution, and tensile behavior, now more on fatigue. We had work, we're completing on corrosion. Grain size effects on strengthening is a fairly recent add. And then a new add in the last year has been alloying effects on texture development. And so today I won't have time to talk about all these, but I will talk about precipitate evolution, fatigue, primarily cyclic deformation, and new alloy effects on texture development. As I said, magnesium alloys can use a little bit higher strength, a little bit higher fatigue strength, et cetera. So we knew that the mag rare earth alloys, have much higher strength than the conventional alloy systems that we're used to. We also know why that is, and it's because so these are precipitation hardened alloys, and the precipitates in these materials are orthogonal to the basal axis. So the primary slip system in many magnesium alloys is the basal slip system. So you'd like to interfere with slip on that system. And so having precipitates that are perpendicular to that slip system is important. Compared with these mag aluminum alloys, when you age those, the precipitates lie in the basal plane. And so then they are less effective at blocking slip. So we know that, and that's why they're strong. But why are these precipitates oriented orthogonal to the basal plane, or actually parallel to the prism plane? And are there other alloying approaches that might behave in similar ways? Because rare earths are expensive, and so we'd like to minimize their use for things like automotive applications. So here's a precipitate, one of our use cases, and this one is on precipitation, where we combine statistical mechanics, DFT into the statistical mechanics, phase field, and detailed high-resolution TEM and atom probe experiments, linked with the materials commons, of course, all to understand precipitate evolution in these mag rare earth alloys. Let me just get out of this a second so I can get rid of this, your poll. Sorry, the poll was bothering me. Now let me get back here. Okay, there we go. There we go. So anyway, in the center of this figure, so the primary precipitates that we're thinking about here are metastable precipitates. So we can't use CalFad because they're not, these particular rare earths have not been assessed in the metastable phases, haven't been assessed. And in these mag rare earths, there's an enormous amount of controversy about the precipitation sequences in these alloys because they're very, very complicated. So we looked at mag neodymium and mag yttrium as sort of our prototypes for where to start. Mag neodymium has these sort of lenticular precipitates that are orthogonal to the basal plane and parallel to the prism plane. Prior to this, people were talking about beta prime, beta double prime, and DO19 type precipitates. But what we, using CHASM, we did some very detailed studies of these systems and actually came up with this new nomenclature called beta triple prime. And it was based on this observations in high-res TEM of very repetitive structures within a given precipitate. So we have these rings that are like DO19, then these sort of checks and W's that really are indicative of local compositional fluctuations along this very tiny precipitate. And so that led us to propose this as the phase diagram for these neodymium type alloys. So it's basically a continuous sweep of different types of beta triple prime across the entire composition domain from sort of 0.15 in this case to 0.25. So we've identified this new and we think consistent phase, if you will, and its 3D morphology. Then we used CHASM, and by we, I mean Anton van der Ven and his then student and postdoc, Anirudh Natarajan, who did high throughput CHASM simulations and determined that these magneodymium prototypes, beta triple prime, are shown here in gray. So a number of elements meet that model. And then the silver atoms are like mag-yttrium and form beta prime S, which is more like this phase in the center of this phase diagram if it were mag-yttrium. And this all has to do with the stress-free transformation strain of these particular elements in magnesium. And Anirudh was able to calculate that and propose this is the primary mechanism. Then we did use those strain-free transformation strains, stress-free transformation strains, and interfacial energies to drive in the free energies from the phase diagram to drive prisms PF, and in the magneodymium alloys, we saw these lenticular precipitates form. We predicted them to form, and in the these mag yttrium type alloys, the beta prime S, which are rod type like precipitates. We've also extended this now because, as we said, one of our goals is to understand alloying. So looking at ternary and then quaternary alloys, we could determine that, in fact, yes, yttrium segregates to the beta prime alloys. Here's some high-res TM of Shenyang Xia in the center. And the beta triple prime neodymium segregates to this, although it's not, there's elements of it present in both, obviously, but also calcium segregates equally between beta triple prime and beta prime. And this was also predicted by CHASM that indicates that calcium occupies rare earth sites. And in addition, the calcium tended to accelerate aging. So we look at calcium as a promising alloying element and at least a partial substitute for some of the neodymium elements. And then we are able to map these phase field results shown here, these maps of phase field, to Paradis to do dislocation dynamic studies on precipitate spacing. And so then we've linked that with crystal plasticity to predict precipitate effects on strength. And I won't have time to go through that, but there's a number of publications here that are available if you are interested in that area. What I will talk about, so in a similar vein, we've been looking at fatigue behavior. And one of the things I want to talk about in this use case is cyclic twinning and detwinning during fatigue loading. So to set the stage for this, I need to remind you of some of the complexity of magnesium. It's hexagonal close packed. And of course, as I mentioned earlier, we have deformation modes. The primary deformation mode is basal slip on the basal plane, 112 bar O slip direction. We can also have prismatic slip. It's a little bit more difficult, and pyramidal slip to get along the C-axis, which is a lot more difficult in many magnesium alloys. And then, of course, in HCP materials, twinning is a very, very important deformation mode as well, which adds to the fun. So if we have tensile stresses along the C-axis in a particular grain, then these slip modes can be activated if everything is set up right for that. To look at the literature, if you will, of the critical resolve shear stresses in pure mag and unalloyed mag. This is kind of where we think we are in the literature. So this basal slip is around 3 megapascals, 36 MPa for prismatic and 86 for pyramidal. So this balance of, or this ratio of pyramidal to basal slip is a very important parameter. The higher this is, the more difficult obviously it is to get pyramidal slip, and this can lead to ductility problems and formability problems because of slip anisotropy, generally deformation. And so the literature has suggested this is about a ratio of 30 to 1, 29 to 1. And we think this is pretty reasonable from the literature. Less clear is twinning. Literature sort of suggests it's around 20 MPa, but there's kind of limited detailed literature around that. And so a lot of this has to do with calibration of crystal plasticity models. That's where a lot of this has been derived. And so I'll talk more about these values as we go, but just wanted to sort of set the stage around that. Now, because these materials are so anisotropic, have so much anisotropy, the deformation modes are very dependent on the texture, and very frequently in pure mag, as well as mag aluminum and sort of a lot of the conventional alloys, we get a basal texture either during rolling or extrusion. And most of our results are on extruded material, where this would be the extrusion direction and then the radial direction. And so we see this very pronounced basal texture. Now here we've sort of tried to depict what happens. So if we're loading along this extrusion direction, the basal planes are oriented orthogonal to that extrusion, this direction. And if we load it in compression, then we're actually getting Poisson's effect that load the planes that induce twinning. And so then we get twinning that flips basically 86.3 degrees within a given grain. We can get, and I'll show more micrographs of that in a bit. So these twin planes orient at roughly 90 degrees. And then if we load in compression and tension, we reverse that. Then these twins detwin and flip back. So this is well known, or reasonably well known in the last maybe 5 or 6 years phenomenon, but quantifying it and modeling it, and in particular, we're interested in alloying effects, is a bit more difficult, or a bit more timely, I guess. And so this is what happens because of these this slip anisotropy. So this is a typical hysteresis loop. In this case, this is a mag aluminum alloy. Should be up here. Sorry, it's not. At any rate, so if we start loading in compression, we get twin initiation. Then we're out here and we reverse the load. At a certain point, we get complete detwinning. Then we get normal deformation modes through a basal or prism slip. And then we reverse that. And so you can see a couple things. You get this funny shaped loop. You also see the peak, and these are constant. These are to balance strain. So this is the strain in tension as in compression. And so this strain in compression goes to 94 MPa, whereas in that same strain in compression gives 192 MPa. So this can have significant effects on how damage is accumulated and how you account for cyclic deformation. And so that's why this is of interest. So we started looking at this at using synchrotron research at Chess. And this is the work of Ariel Murphy, now Leonard. She was a student in the center, and now at Ohio State. At any rate, Ariel did high energy polycrystalline diffraction of these tensile fatigue samples. And saw that and this is basically looking at this twin peak, so no activity until we got to a certain compressive load, then reverse load, and we saw detwinning. So she could qualitatively understand twinning and detect. We could correlate, not correlate, we could relate this directly to a compressive stress and a tensile stress over here. So we could quantify the twinning and detwinning stresses. However, the volume fraction is more problematic using this particular HEDM technique. We do a lot of work calibrating crystal plasticity models with this, or using crystal plasticity models to model this. And this is an example of our prism's plasticity for this mag for aluminum, showing the fidelity of our model here and the experiments. And now one of the problems, as I said, we can't really quantify the twin volume fraction using this particular HEDM technique, but we can qualitatively using, so we have a very advanced twin detwin model in the prism's plasticity code. And so now we can quantify the predicted twin volume fraction, and at least it lines up pretty well with Ariel's results from HEDM. Another thing that Ariel discovered were that these twins are what we call cyclically persistent. So people that study fatigue know that slip bands can be persistent, but twins also can be persistent. So this is looking at some experiments where she compressed, and this was, everything here was done at zero load before or after a compression or a tensile cycle. So she compressed this, then unloaded it and saw the twins. Then she loaded it at tension, looked at it again at zero load, and saw the twins had disappeared. Then loaded it in compression and unloaded and saw the twins in almost exactly the same location. There are a few additional ones here, but pretty much in the same location. So this twinning is persistent cyclically. The problem is, in terms of quantifying twin evolution, you need to do this under load, and that's difficult. So we developed, with the help of a colleague, Chris Torbett at Santa Barbara, an in situ EBSD characterization technique. So we load it, and then the difficulty here, of course, is getting it close to the 75 degrees. Roughly, you need, well, in this case, it was 53, to get EBSD patterns reliably, and then doing that at different loads. And so this is the work of Jia Shen, a postdoc in the PRISM Center. Let's see if I can get this to go. So yeah, so this is loading and compression. So we see twins forming in the EBSD pattern on the left, and these are the variants that are, he determined these to be. So there are 6 variants in twinning, and so he's able to determine that. And I won't draw your attention to this thing on the right. That's a detail we won't have time to get into. But then we can continue to go under load. You see the twins grow, so they widen. That's the twin growth that's going on, and get fatter. And then we unload, and they start to shrink and reload, and they start to appear in exactly the same place. And we can now determine these variants. We can do these same sort of experiments now in PRISM's plasticity, and estimate or predict the volume fraction, the variance and the volume fractions of twins. So we've done these kinds of experiments for a couple of different alloys now. This is fairly recent results. Looking at pure mag or unalloyed mag and mag for aluminum. We really don't see a lot of, if you go to here 0.03, maybe it's 35 volume fraction of twins. Here at 30, it's about 35. But this is clouded, so there's no significant alloying effect on twinning. And the literature on this is kind of spotty. Some theorists proposed that there are no effects. Some have even theorized that alloying can lead to reduced twinning strains. So this is an important issue for us. But however, quantifying this is clouded by this differences in texture that are natural. So PRISM's plasticity provides us a means to account for these texture differences. So we have modeled this, all these experiments as well in PRISM's plasticity, and use this sort of hybrid sort of MTS cyclic stress strain, in situ twin volume fraction and prism's plasticity to determine the critical resolve shear stresses in mag and mag aluminum. So in the pure mag, what we believe are values that we would propose, we have pretty much said, yeah, the literature's right in basal, prismatic, and pyramidal, but it's very high for the twinning, and this is the growth stress, not the initiation stress. It's a little bit lower than that, but so then we've also done the same thing in mag for aluminum. So as we might expect, solute hardening increased basal slip. It increased prismatic slip a little bit. Actually, it decreased pyramidal slip, but it also substantially increased twinning. So this is a really, we think, important finding that alloying actually does increase, at least for for aluminum, it does increase the twinning resolved shear stress. Also, we see that it decreases the pyramidal to basal ratio. And this is a very important for understanding texture and plastic anisotropy. And I'll talk a bit more about that in a little bit. And when we do all that right, we get well predicted loops. So this is our unalloyed mag. We see these flat loops, and then in the mag for aluminum, we see these really interesting sort of very high anisotropy loops. Let's see, how am I doing on time? Okay, we're more or less where I think we need to be. I wanted to talk, so I mentioned that it's difficult to quantify twinning using HEDM. And one of our students, Duncan Greeley, took that challenge on, and again, some experiments at Chess, where he did a combination. So there's a technique called RAMS. It's a very tiny sample, about 1 millimeter on a side, loaded, and you can look at use far field diffraction to look at the elastic strain tensors in each grain and the orientations and the center of mass. But then they also have the capability to do near field diffraction, a technique developed by Bob Suter et al. At Carnegie Mellon, to do a very precise map of the grain size, shape, and orientation and grain location neighborhood. So we can really get a very detailed 3D map of the grains and their deformation. And so, as I said, Duncan took this very complicated challenge on to quantify twins in each grain. And so here's a particular macroscopic stress strain response. And he said, well, okay, here this grain 547 starts to twin. Twinning is completed, then twinning is detwinned in that particular grain. And he can also determine the variance in each of these. And this is sort of a map. So magneodymium has what's called this rare earth texture. So it's a weaker texture. So we actually don't see nearly as high a twin volume fraction in these alloys because of its weaker texture. And so these alloys tend to be more formable. So he said, here's the 687 grains total that he imaged. 187 of these twin. 165 in tension and 27 in compression. And so he can tell which particular grains have which particular orientation and so forth. So then he had the cumulative twin volume fraction from all grains. And as I said, here the twin volume fraction is low, which made this a pretty difficult experiment. So kudos to him for completing that. And here's a 3D map of these local twinned grains. So now we can start thinking about and mapping of the variance. So now we can start thinking about how neighborhoods affect twinning in these alloys. So because we now have a precise 3D reconstruction of this volume of element, this 1 millimeter cube. We can map that to our crystal plasticity model directly. And so that's shown here, and then do prism's plasticity, cyclic stress strain. Again, now here for inputs to the crystal plasticity model, we'd love to do DFT DFT models, but there's not very many except for Dallas Trinkle at Illinois has done it for all elements for basal, but less is known so far for many of the other alloying elements and the other slip systems. At any rate, Dallas suggests that it should be 9.5 MPa, and we chose 9. We didn't have values for these others, so we had to calibrate that from the far field results from the prismatic data and twins. The twin, you can detect the twin critical resolve shear stress as well from the far field data. And so now you see prismatic at 35, pyramidal we estimate at 95. So and twinning has gone to 45. So importantly here, now we're seeing a fairly substantial increase in twin critical resolve shear stress due to neodymium, even though we have a low number, so that's difficult to quantify, but we feel that's a pretty reasonable estimation. But also importantly, we see pyramidal to basal ratio is 10:1. So again, this is part and parcel of why these alloys have a lower texture. Okay, and this is something that will be getting out soon. We have a manuscript in progress on this. So let's see. Okay, so I've got a couple of little segments I want to talk about here still. So texture evolution. So this is a new thing for us, and here we're combining all of the tools to predict texture evolution in these magnesium alloys. And this is particularly important for sheet formability. So magnesium alloys are very difficult to form at any kind of reasonable temperatures and strain rates. And so formable mag alloys, these rare earth alloys are formable, some of them, and that's because they have this softer texture. And we had the opportunity to work with USAMP to work with some of these alloys. And to get a formable alloy, you need to have this very reduced, instead of these pronounced basal textures, which these can be even, a pronounced basal texture would be like 12 or 14. But in these now rare earths or mag zinc calcium alloys, what we've discovered, also have these soft textures. So zinc or calcium alone don't do this, but zinc and calcium in combination provide these very weak textures. And as I said, this is very critical for sheet formability. And this is some recently published work of Tracy Berman in the center. And so looking at as deformed texture and annealed textures. And so you can see here going through a range of alloys. We can soften this as deformed texture. And we think primarily this is because of this changing of ratio of C+A, prism slip, pyramidal slip, I'm sorry, to basal slip, that ratio. But another important part of this is the recrystallization after deforming. So she did all these experiments using a Gleeble to simulate rolling. These are very complicated 10-step rolling simulations, followed by short anneals. And we've theorized that this was because of this reduction in sort of the ratio of pyramidal to basal. We've recently, this is the work of Mohammad Reza Yahoubi, who's our Prism's plasticity staff person. And so he can, arbitrarily in the simulation, change the ratio, the critical resolve ratio between. So here he's simulating magnesium and mag calcium, and you see the traditional intense texture develop. And over here, what we think is going to be the right ratio for the zinc calcium alloys. And we see this splitting along the rolling direction for the as deformed structures. So this pyramidal to basal slip is very, very important. However, also very important is, so this is one of these formable alloys that didn't have quite as soft a texture, but it's still a much reduced texture intensity. But then we can, by recrystallization, this is grain orientation spread from EBSD that shows the amount of recrystallization. So when we have full recrystallization, we can get the desired texture. So that's some work that we'll be doing over the next several years, trying to really understand that. Again, an important part of this will be linking Prism's PF and Prism's plasticity directly to do recrystallization analysis. Okay, I see my time is coming to an end, but I do have one more quick topic. And that's the materials commons. So the materials commons is another part of our open data, open sharing idea. And so the idea is to make this easy. So it's never easy to share your data. It's always sort of a pain. And we're trying to make this as easy as possible. And if we share more data, if everybody shares data, then we believe that this will accelerate model development and validation. So whether you have any interest in any of the Prism's software or magnesium, hopefully you're interested in sharing data, and you can use the materials commons to do this. So if you're a grad student, this is a place to house your data and find your data at the end of 5 years or 4 years or whatever. What did I do on day one? Here's where your data. If you're Adam and your student has graduated, and 2 years later you said, where is that data? You could find it on the materials commons. And so we've been through 2 iterations of this. This materials commons 2.0 was launched in a little over a year ago. And it's basically sort of an electronic lab notebook, a collaboration platform, and then when you choose to publish it, a public data repository. And there's the address there. So we abide by the FAIR principles. That's all data scientists now are talking about the FAIR principles. So findable, accessible, interoperable, and reusable. And so we, if you publish the data, here you can print a DOI. It's searchable with Google data sets, et cetera. It walks you through establishing the metadata that makes it reasonable to find the data and to understand the data if you've found it. We put a lot of activity into trying to make this easy and useful. And we've got a lot of documentation training. Again, you can look at this on the YouTube and so forth. And if you have HED and these large high energy diffraction method data sets, then Globus is something you want to maybe use to upload these large data sets. So this is an example of this recent work that Tracy Berman completed on mag zinc calcium textures. And so now this is a public data set. So she's got a little description here of the data set, their files and samples and workflows. But just to give you an example of what you can find there and what she uses daily to find data. So here's a particular sample, and she can determine, well, I did EBSD on this, I did Gleeville, I did microscopy, here's my received sample, and I did texture analysis, and even look a little bit deeper. Here's the texture, here's the compositions, and so forth. So we think this is a very useful tool. Then the last thing I want to mention, that we're trying to establish communities of practice around specific activities. So we have these around CHASM, Prism's plasticity, phase field. We have one that's just starting to form around recrystallization, and one that we've sort of proposed around HEDM methods. And certainly if you have your own particular technique, whether it's in magnesium or steels or ceramics or polymers, you can establish your own sort of community of practice using the materials commons, so it's freely available. We also just plug for our annual workshop. We haven't been able to do it for 2 years, but I'm hoping that we'll be doing it this coming August. So by all means, check out our website, send me an email or whatnot. So with that, I'd like to thank you for your attention and summarize here by saying PRISM Center, we're providing high performance computational tools in our framework for next generation ICME or MGI. Our integrated scientific use cases are providing new insights in magnesium and mag alloys, precipitate evolution and new alloys, cyclic twinning and detwinning and texture evolution, and then much more that I didn't have time to talk about. And we certainly hope you'll use these open source tools and add to them as Kubra is doing, and establish your own materials commons community. So with that, I'm happy to answer questions.
Thank you for the great talk, Professor Allison. So, okay, I think there's a question already. Please go ahead.
Do you know when the recordings of these lectures are going to be posted? There was a lecture, well, both this lecture and the lectures from previous weeks. I'm afraid I couldn't find it on YouTube when I looked. So
Sure, I will put the YouTube the whole list in the chat in just a moment.
Okay, do you have a question to Professor Allen? I check if there is any. I don't see any questions yet. No questions so far.
It's a quiet bunch.
I think it was a very great talk. No one has a question. Okay, so please go ahead, Professor Powell.
Sure. So it's very interesting to see how there are kind of different interactions between elements. You showed the example of calcium and zinc, and I wonder if are there others that you think that that are noteworthy in terms of multiple elements where the individual elements don't have a particular effect, but combinations of them might?
Well, certainly in the literature, calcium is a really important actor here. So calcium, in connection with many of the rare earths, have shown similar sorts of interactions. So the calcium atom is a larger atom. I think I get this right. And the zinc atom is a smaller atom. And so we think it has to do with this size ratio. That's part of it. And that's where we think it's impacting slip. They also co-segregate. So calcium and zinc also co-segregate to grain boundaries. And we've got some really fun data. I didn't have time to include that on calcium and zinc co-segregation. So calcium alone or zinc alone don't tend to segregate as much. But if you have them both, then they co-segregate. And we suspect this may have something to do with this recrystallization phenomenon. But we're very early days on that. Yeah. But I think calcium and many rare earths do similar things. Those are the ones I'm familiar with. I won't say I've got exhaustive knowledge on that, but yeah.
Interesting, thanks.
Yep.
So no more questions. Oh, Aditya. Okay, please go ahead.
Hi, Professor Allison. Thank you for your talk. My question is, do you have any benchmarking standards for these models in terms of multiple, I guess, groups sort of trying to work on the same problem or otherwise?
It's it's an interesting point in terms of like round robins or benchmarking. Many people have worked on unalloyed mag. So there's a fair amount of literature there. There's a lot of literature in mag aluminum alloys, but typically what we find in the literature are more commercial alloys. So then they might be zinc aluminum or zinc manganese alloys. And so those, it's a little more spotty. And so there's two other things that make this very difficult. And that is first grain size, making sure you have the sort of consistent grain sizes among materials. We've had to do a lot of work, I didn't talk about that, to sort of make sure that we understood grain size effects as we're doing these calibrations. And then also texture. So if the processing details are different, then you can have these texture differences. So it makes this a little trickier. Yeah, it would be wonderful to have somebody take on, you know, providing an enormous supply of data that many people could do. Certainly on the use of tools, that's one of the reasons that we are so, you know, adamant about making our tools open source. So at least that way you can use the exact same modeling parameters and so forth. And so that's why we certainly encourage people to use the tools at least in a consistent way. So yeah, good question.
Thank you, Professor.
Yeah.
I'll just show the poll results for John's benefit. So phase field is the winner of phase diagrams, but all of them had significant following. Phase field, the winner was no less than twice the two that are farthest behind. So
Okay, good. That's wonderful.
Yes.
Yeah.
broad interest in all of the FRISM's tools. So.
Well, they're there, and as I said, there's training videos on YouTube, so go for it. We discovered last year, so we did our workshop. We had to skip it the first year of COVID, but last year we did it as a video workshop, a YouTube, a Zoom training, and we had almost 3 or 4 times the normal attendance. So we're very pleased with that, and we'll probably redo that. We're not exactly sure what the periodicity that will be, but I'm sure we'll be reproducing that or redoing that. So, and so Kubra, maybe you can come be part of the teaching team next time and talk to us about your implicit solver. So,
I will be happy to help.
Yeah.
Okay, Professor Lados has a question. Please go ahead.
Oh.
Hi, John.
Hi,
Good
Diana.
afternoon. Great to see you again. Wonderful talk as always.
Likewise. Thank you. Good to see you.
John, quick question. Of course, you know I'm going to ask that. How far along are you guys into the Prism fatigue part of the Prism family?
Yeah. So there's 2 parts to this. So obviously not as far along as we'd like to be, or else I would have talked more about fatigue results. We do have a lot of quantitative experimental work. The modeling, both in terms of alloying effects on low cycle fatigue, we have ultrasonic fatigue as you do, and ultrasonic fatigue effects on crack initiation, high cycle fatigue, alloying effects. We've also done a lot of work there on small fatigue crack growth, looking at facets. And so we're about ready to publish predominant facets on fracture surfaces. The trick, of course, is the modeling part of that. And so that's why we were really excited to collaborate with Dave McDowell on this PRISM's fatigue. So he has, of course, perfected the art of fatigue indicator parameters. And so now you can automatically link sort of slip band level fatigue indicator parameters with PRISM's plasticity. And so there's several papers on that but using aluminum benchmarking problems. And Now we're excited to start doing that in magnesium. Then the other part of the problem is the really difficult part of this problem is meshing cracked surfaces. And we've got some collaborations with Ashley Spear at University of Utah, who is working on techniques for meshing fracture surface profiles. And we're hoping to mesh that or use the fatigue indicator parameters as well on the cracking side. So yeah, not as far along as we'd like to be, but certainly we're bending several picks on that problem. And so stay tuned.
Yeah, thank you very much.
You bet.
Appreciate it.
Yep.
Okay, it is already 1 p.m. and it looks like there's no more questions. It looks like it is time to end the session.
Okay, great. Well, again, I appreciate the invitation and the opportunity. So
Thank you for joining
Thanks
again.
very much. Very interesting seminar. Right.
thank you.
Thank you very much.
Bye. Have a good week, everyone.
Bye.
Great. Bye.